हेलो स्टूडेंट्स। मैं डॉक्टर अंजू अग्रवाल। आज हम एमएससी केमिस्ट्री सेमेस्टर थर्ड के न्यूक्लियर केमिस्ट्री के पेपर में गामा ट्रांजिशंस के बारे में पढ़ेंगे। एन अल्फा और बीटा डीके may leave the product nucleus, means the daughter nucleus, either in its ground state or more frequently in an excited state. Excited states may also arise as the result of nuclear reactions or of direct excitation from the ground state. The phenomena that occur in the de-excitation. Now we deal with the phenomena that occur in the de-excitation of excited states. So what is the de-excitation processes? A nucleus in an excited state may give up its excitation energy and return to the ground state in a variety of ways. The most common de-excitation process is the transition is by the emission of electromagnetic radiations or emission of photons. Such radiation is called gamma radiation, and this transition is called gamma transitions. The gamma rays have a frequency determined by their energy E equal to h nu. Frequently, the transition does not proceed directly from an upper state to the ground state, but may go in several steps involving intermediate excited states. Gamma rays with energies between a few thousand electron volts and about 7 mega electron volts have been observed in radioactive processes. And the gamma emission may be accompanied or even replaced by the another process, that is by the ejection of electrons from outer orbitals, that is by the process of internal conversion. The emission of internal conversion process electron comes about by the purely electromagnetic interactions between nuclear and extra nuclear electrons, leading to the emission of an electron with kinetic energy equal to the difference between the energy of nuclear transition involved and the binding energy of the electron in the atom. The third is an uncommon mode of de-excitation. If and this is possible, only possible if the available energy exceeds to the 1.02 milli electron volt. This energy is equivalent to the mass of 2 electrons. It is possible for the excited nucleus to create simultaneously one new electron and one positron and emit them with kinetic energies that total the excitation energy minus 1.02 mega electron volt, and this is an uncommon mode of de-excitation. All the processes described above we call gamma transitions, although only in the first means A. In the A is a, a gamma ray emitted by the nucleus, and all are characterized by a change in energy without change in Z and A. If a nucleus changes and from an excited state to ground state or another excited state to lower energy, the photons are emitted, and this can be explained by the following decay scheme of AU 198. In this case, AU 198 it changes into the by the beta decay, accompanied by the beta decay, the 198 mercury. The half-life of AU 198 is 2.696 days, and in this figure or in this diagram we can say that there are the ground, this is the ground state of daughter nuclei, and this is the first excited state of daughter nuclei and second excited state, and with the 98.7% probability, 198 AU changes into the first excited state of the daughter nuclide 198 Hg, which have above the ground state, having the an excited state energy 0.412 mega electron volt, and with 1.3% changes into the second excited state, which is 1.087 above the ground state of daughter nuclei, and with 0.025% from probability to the ground state, डायरेक्ट तो यहाँ से यहाँ तक to the ground state. Accordingly, we can see the three gamma transitions are observed. First, from second excited state to the ground state. Second is the second to the first, and first excited state to the ground state. In all cases, we can see that gamma rays 1.087, this is the 1.3% of percent change into the second excited state, and 20% of 1.3% is changes directly from second excited state to the ground state. Only 20%, 1.3% to 20% of the 1.3% means 26% of 1.3%, and with 1.087 above the ground state. And second gamma transition with the energy 0.676 means the 80% of 1.3 of gamma radiations. This is equal to 1.04%. And third is the, and this is converted from second excited state to the first excited state. This is the second excited state to the first excited state, the gamma radiations, 0.676 mega electron volt, and gamma radiations 0.412, 98% at this level, and 80% of 1.3% means 1.04%, यानी 99.74% गामा रेडिएशंस जो है हैविंग द एनर्जी 0.412 mega electron volt. And by the study of this scheme, we observed three gamma transitions, and almost all gamma rays means 99.74% emitted by a certain nucleus are monoenergetic, that is, they have well defined energies. Because the recoil energy is transmitted to the nuclei by emission of gamma rays, ray photon are very small compared with the energies of the difference in the excitation energy. Compared with the energies of gamma rays, the latter are practically equal to the excitation energies, or the differences in the excitation energies of the nuclei, E gamma equal to delta E. The gamma spectroscopy is therefore the most important tool for studying the properties of atomic nuclei. Lifetime of excited states. Generally, the lifetime of excited states is very small, of the order of less than 10 to the power minus 12 second, and the gamma radiation is emitted immediately after the proceeding of preceding of alpha or beta decay. If immediate gamma radiations are forbidden because of high difference of the nuclear spins of the excited state and the ground state, in combination with the laws of conservation of nuclear momentum and of parity, a metastable state or nuclear isomer results, which decays with its own half-life. Decays with its own half-life. With its own half-life, and that the transition from the metastable isomeric state into the ground state is called isomeric transition. Isomeric transition is free from accompanying alpha or beta radiations, and some nuclear isomers are of great practical importance as pure gamma emitter. For example, 99M.Tc has found broad application in nuclear medicines. In a number of cases, more than two isomeric states have been found for a given A and Z, atomic mass and atomic number. For example, the radioactive species of half-lives 60 days, 1.6 minute and 20 minute, and 20 minutes have been assigned to SB, SB 124. If there are two or more excited isomeric states, they are labeled by M1, M2 or so on in order of increasing excitation energy. Thus the isomers of 124 SB are denoted as 124 SBG. G is the ground state with half life 60 days half life. 124 SBM1 means this is 1.6 minute, and 124 SB M2 20 minute. We do not consider each isomeric state as an individual nuclei, as an individual nuclei. And similarly, if there are the two one isom, these are the isomers, the this can the M is characterized in is by M after the atomic number. So cobalt 60 metastable state and in the ground state. This is the in the ground state. Most of the books follow this type of characterized the metastable state by this type. In the and we have discussed the connection between the transition probabilities or half-lives for gamma decay, decay energies and spins, and parities of initial and final states. The systematics of isomer lifetime and their dependence on energy and spin changes was important in the development of nuclear shell model. And in discussing half-lives for gamma transitions, we are concerned with half-lives, partial half-lives, since beta decay, and in heavy elements, alpha decay often compete um, with the isomeric transitions in decay of metastable states. आज के लिए बस इतना ही. धन्यवाद.